All right, on 29, let's see, what do the directions tell us to do? They tell us to sketch the region whose area is given by the definite integral, and then use a geometric formula to evaluate the integral. On 29, we're given that integral, okay? So we know that the interval for our region starts at x equals -1 and ends at x equals 1. That's the lower bound and upper bound of our lower limit of integration and upper limit of integration. Okay, -1 is the lower limit of integration, 1 is the upper limit of integration. Then you have to graph 1 minus the absolute value of x. Well, the graph of 1 minus the absolute value of x looks like that. Okay? So that's the region they want us to find the area of. So it's a triangle. So its area is 1/2 base times height. The base would be from -1 to 1, so that's 2. The height is 1. Remember, the height has to be perpendicular to it. So it would be, like that. That would be the height. So 1/2 times 2 times 1 is 1. What's next? 45. All right, let's see here. What are we doing on 45?
What is the one with the area of attractivity? We have sides, not separate ratios.
Yeah. Let's see. 45. The directions for 45 say to use the table of values to find the lower and upper estimates of. All right, so here's the table of values. And we're supposed to find the upper and lower estimates of this integral. So we start at 0 and we end at 10, which is what they have in the table for us. Okay? Now, if we're going to do the lower, let's see. What did I do here? Well, let's talk more in general first. In each one of these, so we've got this. Start at 0, end at 10, but we don't know what that looks like. Okay, but we got some kind of graph there of f of x. It might look like that. It might look like that. That. Who knows, right? But we do know this much. From 0 to 10. And then we're given some points to work with here. So, for instance, we've got the point 0, 32. We've got the point 2, 24. Then we've got 4, 12. Looks like maybe I can squeeze it in. Yeah, I'll move it over a little bit. Then we've got 6, -4. I didn't say 4, 12. I didn't do that. That. Then we've got 6, -4. Put that there. 8, -20. And 10, -36. All right, obviously not to scale, but I actually wrote -36. I guess y'all noticed that. Okay, so if I make the first rectangle, all right, I'm going to go from 0 to 2, and if I want to make it a lower sum, the way this thing, since this is a decreasing function, that would be the rectangle that gives us a lower sum, correct? So the area of that rectangle is 2 times 24. And then the next rectangle, it's again going to have a base of 2. It would look like that. So that rectangle would have an area of 2 times 12. Now, the next one, okay, I want to do this, but I can't, can I? And have a lower sum. So I've got to go below to here. And so now's when we get that signed area. Since the rectangle's below the x-axis, think of it as having a height that's negative. Now, it doesn't really. There aren't really negative segment lengths. But since that rectangle's below the x-axis, its signed area is going to be negative. Okay, does that make sense? And then the same thing for the next one. So at 8, we'll go down here to negative 20. And then at 10, we go down here to negative 36. Then we add them up. All right? To get the upper sum, we do a very similar thing. It's just that now we want our rectangles to look like this. That gives us an upper sum. We just go to the other end of the interval to get the height. So for the first one, it's 2 times 32. For the second one, it's 2 times 24. For the third one, it's 2 times 12. For the next one, it's 2 times negative 4. And then it's 2 times negative 20. And that's an AP type question. All right? It really is. Okay. What else you want to see? 41. All right, on 41, this time we're given that the integral from 0 to 5 of f of x dx equals 10, and the integral from 5 to 7 of f of x dx equals 3. Then we're asked to evaluate these. So first, we're asked to evaluate the integral from 0 to 7 of f of x dx. According to our properties of integrals, if I have the integral from 0 to 7 of f of x dx, I can rewrite it in parts. I can make it the integral from 0 to 5 of f of x dx plus the integral from 5 to 7 of f of x dx. Now let me stop for a minute. That's not the only way I can divide it up. If I've got the integral from 0 to 7 of f of x dx, our property, remember we had the little c in between them. It was from a to b, then we made it from a to c and from c to b. I can choose any number. I can make it the integral from 0 to 1 plus the integral from 1 to 7. Or I can make it the integral from 0 to 6 plus the integral from 6 to 7. Or I can make it the integral from 0 to 1 plus the integral from 1 to 2 plus the integral from 1. Any way I want. So choose the most useful one. Choose the one where you have information. Okay, so that's the reason I divided it up that way. Make sense? All right. And again, why can we do that? Because integrals, the definition of the definite integral is it equals the limit as n approaches infinity of the sum from I equals 1 to n of f of x dx. With sums, you can break sums into separate parts, get the sum separately, then add them up. With limits, you can break the limit up into separate parts, get the limits, add them up. Since the integral is made up of those two things, then integrals must work that way as well. And they do. Okay? So once I've decided that's the way to rewrite this, then it's just a matter of substituting in the given information. The integral from 0 to 5 of f of x dx is 10. The integral from 5 to 7 of f of x dx is 3. So we get 13. Part B. We want the integral from 5 to 0. That's another one of our properties. The property says that the integral from a to b of f of x dx equals negative the integral from b to a of f of x dx. So whenever you're flip-flopping your limits of integration, just change the sign. Okay? So to make it to 5 to 0 then is the same thing as the opposite of the integral from 0 to 5. And I know the integral from 0 to 5 of f of x dx. They told us it's 10. Another property comes up here in part C. The integral from a to a of f of x dx equals 0. So the integral from 5 to 5 of f of x dx equals 0. The reason for that is there's no region. Okay, there's just a little line segment. Line segments don't have areas. And then on the last one, since we just talked about how the definite integral is defined to be the limit of a sum, we can factor constants out of sums, we can factor constants out of limits, so we can factor constants out of definite integrals. So I factor the 3 out, set it in front, then it's a substitution problem. Does that help? All right. What's next? 49. All right, on 49, let's see. Consider the function f that is continuous on the closed interval from -5 to 5, for which the integral from 0 to 5 of f of x dx equals 4. Then evaluate each integral. So for part A, we have the integral from 0 to 5 of f of x plus 2 dx. Well, use your properties. Make that the integral from 0 to 5 of the first term plus the integral from 0 to 5 of the second term. All right, we're told the integral from 0 to 5 of f of x dx equals 4. And one of the few we actually know how to evaluate the definite integral is the definite integral of a constant. Okay? Because we know what it looks like. That's f of x equals 2 from 0 to 5. We get that rectangle. The area of the rectangle is base height. So that's how I know that's 5 times. Okay? And then we get 14. Does that take care of A? Okay. For B, we want the integral from -2 to 3 of f of x plus 2 dx. All right. F of x plus 2 is a, let me get this right, horizontal shift. Remember from pre-cal, maybe? Okay. So that's the same thing as the integral from 0 to 5 of just f of x. All right? F of x plus 2 is a horizontal shift to the left. It just took the whole graph, shifted it 2x coordinates to the left. 2x coordinates, is that 2x coordinates to the left. Okay? And so shift it back. Shift it 2 to the right, make it just an f of x, and that gives us the integral that we already had to start with. So that's not even a calculus problem. That's a pre-cal problem. Or an algebra 2 problem. Is that algebra 2? Probably becoming algebra 2. And y'all thought algebra 2 was hard when y'all took it. All right. Then next, we need to remember for C and D what even and odd functions are. Even functions are symmetric to the y-axis. All right. A good example of that, symmetric to the y-axis, would be like a parabola like that, symmetric to the y-axis. Okay? And if that's the case, the region from -5 to 0 and the region from 0 to 5 are going to be mirror images of each other. So they're going to be the exact same size. They're just reflections of each other. Okay? So when we're trying to find the integral from -5 to 5 of this even function, we could think of that as the integral from -5 to 0 plus the integral from 0 to 5. Well, we could think of it that way anyway. And then, since it's symmetric to the y-axis, they're the exact same size. And so, since we know that the area of that one's 4, then the area of that one's also. Make sense? Okay. And then for D, we need to remember that the odd function is symmetric to the origin. That would be more like this. Okay? And so if I have a region from -5 to 5 again, look what's going to happen. That region, the red one, and the blue one are mirror images. Oops, why'd I do that? Are mirror images of each other, right? But the blue one's going to have a positive signed area, whereas the red one's going to have a negative signed area. Okay? So when that happens, that integral is going to be 0. That doesn't mean the area is 0. The actual area would be 8 again, wouldn't it? Because we know we're given that the blue area is 4, so the red area would have a signed area of -4. And we just have to remember, okay, that's the signed area. It's all below. If I really want to know how much area it is, it's 4. So we're not saying that that region just doesn't exist. All right, we're saying that half of it has a signed area that's negative. The other half of it has a signed area that's positive. They're equal. The absolute values of those are equal to each other. So the total of the integral is 0. I mean, the actual area would be 8, but the integral is 0. Okay? So that's a case where the integral does not represent the actual area of a region. All right? So, writing it out calculus-like, using calculus to write it out, you would say that the integral from -5 to 0 of f of x dx is the opposite of integral from 0 to 5. So that would give us that, which in turn gives us that. That was a good problem. That's another thing. That's also a little bit AP-like. All right, what's next? 47. Woo, I like this one. This is so AP-like, I can't even emphasize it enough. In fact, I'll guarantee you there will be a question like this on the AP test. Okay? I mean, it just is. All right, on 47, it says the graph of f consists of line segments and a semicircle, as shown in the figure, and which I did an awesome job duplicating on my paper. Thank you. Evaluate each definite integral by using geometric formulas. All right, so for part A, I want the integral from 0 to 2. From 0 to 2. So that's our region, isn't it? Okay? Its signed area is going to be negative, isn't it? Because it's below the x-axis. So the integral from 0 to 2 of f of x dx equals, all right, it's not a circle, it's not a semicircle, it's a fourth of a circle. Okay? So 1/4 pi r squared. Now, why did I put a negative in front of it? Because it's below the x-axis. Okay, so -1/4 pi r squared. And then you just work it out. So far, so good? All right, let's look at part B. Here we want the integral from 2 to 6. So let's get rid of that, and let's go from 2 to 6. There's our graph. So this is our region. So the integral from 2 to 6 of f of x dx is the area of a triangle. And it really is triangle this time. So that's 1/2 base times height. The base goes from 2 to 6, so the base is 4. The height, well, they tell us the coordinates of that point are 4, 2, so the height is 2. So 1/2 times 4 times 2. Still with me so far? Then they want the integral from -4 to 2. From -4 to +2. So from -4 all the way over here to +2. So that would be all that. All right, now, so the integral from -4 to 2 of f of x dx. Let's use our properties. And can't we think of this as a triangle and a semicircle? So let's divide our interval up so that we get a triangle and a semicircle. So let's go from -4 to 2 of f of x dx, then the integral from -2 to 2 of f of x dx. Okay? Now, both of these are below the x-axis, so I'm going to get negative signed areas. So -1/2 base times height, -1/2 pi r squared. Now, let's take care of the -1/2 pi r squared first. The radius is 2, right? That's the center. That's radius. So we get that. Now, I wrote down -1/2 base times height for that triangle. That's fine. I could have thought of it this way. I could have thought of it as 1/2 base times height, and then when I wrote it down, 1/2, the base is 2, and I could have thought of it this way. Since that height goes from 0, y-coordinate of 0 to a y-coordinate of -1, I could have just called the height -1 and worked it that way. I'd get the same thing, wouldn't it? Does it matter? Just don't do both, right? Don't put the negative there and then put a -1 there, because all of a sudden now you're getting a positive signed area, and that's not what you ought to get. So just don't do both. All right, so C makes sense? Silence means C makes sense? Nah, there's no need to make it a decimal. All right, part D, from -4 to 6. Okay, that's the whole kit and caboodle, isn't it? -4 to 6. Now, let's be smart, because we've already done all the work necessary if we just rewrite our integral the right way. We've already done that and got that. We've already done that and got that. So divide it up that way. Okay? So make it the integral from -4 to 2. That's the blue one. And we know what it is. It's -1 minus 2 pi. Plus the integral from 2 to 6. That's the red one. And we already know what that is. It's 4. So add those together, and we have our integral from 4 to 6. Make sense? E. All right, now this gets tougher because they throw in that absolute value. Well, look, you take the absolute value of it, all it does is that. Does it change the triangle on the right end? No. Okay? So break it up the same way. Make it the integral from -4 to 2 of the absolute value of f of x dx plus the integral from 2 to 6 of the absolute value of f of x dx. All right? Now, that's the same thing as, that is the same thing as the absolute value of whatever that integral was originally. Because graphically, all it does is change what I have in pencil into what I have in blue. Okay? Well, we already know what the integral from -4 to 2 is, -1 minus 2 pi. So slap absolute value signs around it. And then we already know what the integral from 2 to 6 is. It's a positive number, so we don't really need the absolute value signs at all there. So you with me to there? All right. Well, -1 minus 2 pi has an absolute value of 1 plus 2 pi. and we're back in business. Okay. And the last one. The integral from -4 to 6 of f of x plus 2 dx. Okay. Make that the integral from -4 to 6 of f of x dx plus the integral from -4 to 6 of the second term, 2 dx. We already found the integral from -4 to 6 of f of x dx. We found it right here. So write that down. And the integral from 2, or from -4 to 6 of 2 dx, I can figure that out. In fact, well, I'm going to show you, I'm going to write it, I'm going to draw it, and then we'll tell you how to do it without bothering to draw it. Be from -4, well, I'll draw it up here. Be from -4 to 6 of f of x equals 2. Oops, I've got a 2 on here. What's the area of that? What's the base? 10. What's the height? 2. So it's 20. Now, even without doing that, look at your limits of integration. What's 6 minus -4? 10. So that times 2 will give you that area. Okay? Ta-da! Making sense? All right. Anything else? 37. All right, on 37. All right, we're given that the integral from 0 to 4 of x cubed dx is 60. The integral from 2 to 4 of x dx is 6. The integral from 2 to 4 of dx is 2. For 37, we have the integral from 2 to 4 of x minus 8 dx. So use the property that says that we can turn this into separate integrals of each term, and then either plus or minus, whichever is between them. So the integral from 2 to 4 of x dx, and then since it's x minus 8 up here, it'd be minus the integral from 2 to 4 of 8 dx. All right, now, we're told what the integral from 2 to 4 of x dx is. It's 6, from right there. To get the integral from 2 to 4 of 8 dx, well, I kind of just showed you how to, didn't I? If you subtract the upper limit of integration minus the lower limit of integration, you get 2. 2 times 8 is going to be it. But when you worked this, yesterday, I hadn't told you that yet. So you factor out the constant, put it in front, and now we're told what the integral from 2 to 4 of dx is. So you've got your 6 minus 8, and then times that integral, and the integral from 2 to 4 of dx is 2. So that's 6 minus 16, negative 2. All right? Anything else? 51. There it is. Let's see. The interval, closed interval from 1 to 5, is partitioned into n subintervals of equal width, delta x, and xi is the left end point of the ith interval. So they want to know, they gave us the sum from I equals 1 to n of f of x sub I delta x, and then we're supposed to say that it's less than, greater than, or equal to the integral from 1 to 5 of f of x dx. So in other words, will that approximation be exactly equal to the actual area, or will it be less than it, or will it be greater than it? Well, since our graph looks like this, and they tell us to use the left end point of the interval. So we're finding left-hand sums. So that means to use that as an interval, that as an interval, right? When it's a left-hand sum, that's when the left endpoint of each subinterval leads to the height. So is that going to be too big or too little? Too big, so greater than. A graph looked like that, and we use left-hand intervals. Then they'd all be inscribed rectangles, and it'd be less than. All right, you head full? There's your assignment.